Okay, we move on to day 6, I believe. Today we'll be looking at section 3.4, linear programming. We'll incorporate everything you've learned over the last couple of days, solving equations, a system of equations, graphing linear inequalities. So everything comes together with this lesson. I've always liked this lesson because it encompasses everything you've learned up until now. So let's take a look at linear programming, and I'll give an example of what linear programming is. But I will say this, it is quite important. Linear programming is used a lot. And for example, in scheduling, like in the NFL football teams and referees and who plays where and so on and so forth, or even airline reservations and what flight attendants go on what flight and what pilots fly and where they fly and all of that. So it's used a lot in scheduling things. Linear programming is really quite important. But here, let's take a look at an example and see what linear programming is. So say, for example, we have Ace Hardware. And Ace Hardware produces acoustic and electric guitars. They earn $30 profit for each acoustic guitar sold and $50 profit for each electric guitar sold. Okay, so profit is what a company makes after they paid their expenses. If you ever ran a lemonade stand, so you would take in money, you'd sell lemonade, but you'd have to buy the materials, the cups, and the lemonade. Okay, and so the profit would be the difference between what you earn and what you had to spend to run the business. Okay, so in addition to profit, to produce the guitars, each acoustic guitar requires 2 work hours in factory A and 4 work hours in factory B. Each electric guitar requires 4 work hours in factory A and 3 work hours in factory B. And each factory operates no more than 10 hours, so they only have 10 hours in which they can operate. And, okay, so Ace Hardwares, or Ace Guitars, I should say, they're going to consider how many guitars should they make to maximize profits. Okay, so they're going to determine that through linear programming. So step 1, again, we define our variables. That's important. And you don't have to worry about many word problems with linear programming for homework, okay? I'm not going to give you any. I'll just give you the nitty-gritty of working with linear programming without word problems. So anyway, first one, define the variables. X will equal the number of acoustic guitars sold, and Y will equal the number of electric guitars sold. Then the profit will be for each acoustic guitar they earn $30, so 30x, and for each electric guitar they earn $50, so 50y. So they want to maximize. So they want to make as much money as possible. So maximize 30x plus 50y. But there are constraints they have to consider. And those constraints are hours available in factory A and factory B. So we write constraint inequalities. So for factory A, each acoustic guitar uses 2 hours. And then each electric guitar uses 4 hours in factory A. So 2x plus 4y has to be less than or equal to 10. There's only 10 hours in factory A. And then for factory B, each acoustic guitar uses 4 hours in factory B, and then each electric guitar uses 3 hours in factory B. So 4x plus 3y again must be less than or equal to 10. They only have 10 hours. And so linear programming works like this, okay? So you define your variables, you figure out what it is you want to maximize, or maybe sometimes you want to minimize something. And then you figure out what your constraints are and you write them, and then you graph them. So we graph the constraints and then we shade the feasible region. So that's already done here for us. So the feasible region is what you see there. If I were to graph those constraints, then there's 4 of them. Okay, there's 4 of them. So this is 1 constraint, and that's 2 constraints, and then both x and y has to be greater than 0. You can't have negative. I mean, you can't They're not going to sell negative guitars. Okay, that just doesn't make sense. Okay, so then we have 3 and 4. So I have 4 constraints there, 3 and 4. And then if you graph them, it looks like that. So you get the shaded region that they give you there. Right? I'm not going to go through how they derive that. It's pretty easy. All you have to do is put those equations in slope-intercept form and graph them. All right, but here's the deal with linear programming. It just so happens that the objective function, whether or not you want to maximize profits or minimize costs, always occurs at these corner points, always. So at the point 0, 0, at the point 0, 2.5, at the point 1, 2, or at the point 2.50. Okay, your objective function is always maximized or minimized at those corner points. Okay, so what we have to do in linear programming, we have to take those corner points and then we have to plug them into our objective function. They want to maximize profit, 30x plus 50y. So when I take 0, 0 and I plug it in, I get 0. When I take the corner point 0 and 2.5 and plug it in, I get 125. When x is 1 and y is 2 for that corner point, I get the value 130. And then when x is 2.5 and y is 0 for that corner point, I get 75. Okay, so Ace guitars then, if they want to maximize profit, they would produce 1 acoustic guitar and 2 electric guitars. And there they would maximize profit. Okay, so we're going to work through some problems. They won't be word problems. We'll work with constraints, and then we'll define our objective function, whether or not to maximize or minimize. And then, yeah. But you'll see that it's going to use everything that you've learned, okay, in chapter 3. So I'll go over 3 problems, and that will be it. You'll have, I'll give you 4 problems for homework. These problems take a long time to do. You have to graph. You have to graph inequalities. You have to evaluate corner points, and you'll see you have to find the intersection between lines for lines. So there's a lot to do with these problems here. That's why I like them, because it uses everything you've done. So let's look at here. So what is linear programming? Linear programming is a method of finding a maximum or minimum value of a function that satisfies a given set of conditions called constraints. A constraint is one of the inequalities in a linear programming problem. The solution to this set of constraints can be graphed as a feasible region. And then we always maximize or minimize the objective function at the corner points of that feasible region. So here you had a problem number 7 in your homework last night from section 3.3, and I've just graphed it again. Okay, actually I used decimals. Okay, but here, so let's take a look at this. So we have 4 constraints. X was less than or equal to 9. So this I'll just write x is equal to 9 here. Where is that? So this is x is equal to 9. But it goes that way. X is greater than or equal to 9. I'll just write x is equal to 9. But notice it is going that way. And then we have the other one, x is less than or equal to 13. So then this equation, that's the equation x is equal to 13. But it is graphed in that way, so x is less than or equal to 13. And then what else do we have? We have y is greater than or equal to negative 18. And here's y is equal to negative 18. Let me give myself some more space. So negative 18, y is equal to negative 18. But again, that's y is greater than, so we're going up that way. And then finally, we have the equation y is less than or equal to negative 4. And here's y is equal to negative 4, but we're going down that way. So our feasible region is all of this here. All of that. Now let's say here we have an objective function, and we want to maximize some objective function. And let's say here that objective function is defined as negative 2x minus 3y. We have to maximize it. So what we have to do is we have to evaluate these corner points. This is going to be quite easy. This point here, we know x is 9. We know x is 9, and y was -4. Okay, that's the answer. So we know that this corner point here was, again, x is 9, and then y is -18. So that's that corner point. And then this corner point here, well, that's x is 13. That's x is 13, and y is -4. In this corner point here, again, this is x is 13, and y is -18. So we take those 4 corner points, that you see there, okay, and we'll evaluate them in our objective function. Our objective function was to maximize -2x minus 3y. So I'll take -2 times 9 minus 3 times -4, I get -6. I'll take -2 times 13 minus 3 times -4, I'll get -14. I'll take -2 times 9 minus 3 times -18, I get 36. And then -2 times 13 minus -18 will give me 28. So if the objective is to maximize this linear programming problem, maximize it, we would choose x is 9 and y is -18. If the objective was to minimize it, we would choose 9 and -4 because that gives us the smallest value. But here I'm saying the objective is to maximize, so we would choose 9 and -18. And again, it always occurs at the corner points. So for example, I'll give you, and you'll see here, so I'll just choose any point in this region. So what is this here? So that is 10, so x is 10, and what is y? -10. And you'll see I'll get a smaller value than 36, okay? So here, so p then would equal -2 times 10 minus 3 times -10. So that would be -20 plus 30, and that would equal 10. Again, it would not be the maximum value. Again, it just so happens that you minimize or maximize your objective function at the corner points, not something within, only at the corner points. All right, so let's look at another example here. So again, this is another problem here, and you'll see why now you're going to have to solve a system of equations. This one was pretty easy to do. You could easily see the corner points on that. That was really easy. Sometimes they're not so easy, so let's take a look here. So here, and again, I think this is problem number 8 you had for homework. So we're going to take a look at this. But remember, we want to graph the feasible region, and then we want to find the corner points. All right, and it just so happens, so my feasible region is going to be this here. Okay, you see the equation y is less than or equal to 7, y is greater than or equal to 2x minus 3, and y is greater than or equal to -1/2 x minus 3. So let's find this corner point here. It's somewhat difficult to do. So it's going to be very helpful if I write in my equations, okay? So my equation here, so I know that this is just the line y is equal to 7. I always tell students, that's 17, Mr. Winston, 7. I always tell students, write the equation next to the line, because you're going to need to. And this green line here, let me see here, so the y, so it goes up to, and it looks like, okay, so it has a positive slope, so that's going to be y is equal to 2x minus 3. And then this line here, this is the line y equals -1/2 x minus 3. So I want to find the intersection. I want to find the intersection, see where the red arrow is? I want to find the intersection between these two lines. So one is y is equal to 7. Y is equal to 7. And the other one is y is equal to -1/2 x minus 3. Well, the nice thing is I already know the y value. Okay, I just have to find the x value. What's the x value? So here, as I told you guys before, the easiest substitution problem you ever have is when y is equal to one thing and y is equal to something else. You just set the y's equal to each other. So 7 equals negative 1/2 x minus 3. Add 3 to both sides and you get 10. 10 is equal to negative 1/2 x. Multiply by negative 2 and you get negative 20 equals x. So my x value is negative 20. Right. Now we want to find a corner point here. Again, I know that the y value is going to be 7, so I can see, all right, but I have a system of equations. I have two lines, y is equal to 7, and then the other equation is y is equal to 2x minus 3. Okay, so that's where those two lines enter. So that's those two lines. Let's find the intersection. Y equals one thing, y equals another. Set the y's equal to each other and solve. Add 3 to both sides, you get 10 equals 2x divided by 2, and you get 5. And that certainly looks right. And so this is 5. And then lastly, we want to evaluate this corner. We want to evaluate that corner point. Well, that's the intersection of those two lines. That's the intersection of y is equal to 2x minus 3, and then y equals negative 1/2 x minus 3. So again, you set y is equal to y. 2x minus 3 equals negative 1/2 x minus 3. Add 1/2 x to both sides, add 3, and what you get, so 2, so you have 2x plus 1/2 x equals 0. When you add 3 to both sides, 2 and 1/2 or 3/2 x equals 0. X equals 0. Okay, so that corner point then is 0. And then if I want to find y, I can just substitute 0 into this equation here to find y, either one. And so that will give me then, so I'll have, so y is 0, so I'll have y is equal to 2 times 0 minus 3 equals negative 3. So my y value is negative 3. So I found all the corner points. Negative 27, 5, 7, and then 0, negative 3. All right, so the objective here then, we said, was to minimize that. So let's take a look at which corner point or coordinate point will give us the smallest value. Okay, so 2 times negative 20 minus 4 times 7 is negative 68. 2 times 5 minus 4 times 7 is equal to negative 18. And then 2 times 0 minus 4 times negative 3 is 12. So if we were to minimize this objective function, we would choose x is equal to negative 20 and y is 7. All right, and so that's it. So I've gone over two problems. They all work the same. You write you have to graph your system of inequalities. You have to shade the feasible region. You have to determine the corner points, and maybe sometimes you'll have to solve a system of equations, which is what we've been doing. And then you have to evaluate those corner points in the objective function. Okay, so you'll have 5 problems to do for homework. I will do one with you so you know how to interpret the homework. I will expect to see this in your homework if I collect it from you, if you're randomly chosen. If you don't have it, I severely take off points because I'm going over this here. So make sure you follow along here. Okay, guided practice. So when I guide you through, I expect to see it on your paper. So what I'm going to do is number 3 for you. You will have to do 2, 3, 4, but I'm going to do number 3 for you, and then 9 and 10. And I'll show you how this works here. So I'm going to do 1 for you, and then you'll have 4 on your own. So I'll do number 3. So this is going to be number 3. So they give you x is greater than or equal to 0, y is greater than or equal to negative 1. Okay, what you see there. All right, so let me do this for you. All right, so the graph is here. So x is greater than or equal to 0. So I know it's going to go that way. And then y is greater than or equal to negative 1. Right, so I have to graph that. And it would be helpful if you have graph paper, okay? Maybe I'll leave some in school, okay? Well, I should, because I always do, okay? I'm just not in school, so, but I'll make sure some is left for you if you're in school. So that's that way. Y is greater than or equal to -1. The other equation is y is, and again, let me write this. So this is x is equal to 0. It always helps. Y equals -1. Okay, and then I have the equation y is equal to x plus 1. So here's my y-intercept there at 1. And I go up 1 over 1. And so up 1 over 1, up 1 over 1, up, or I can go down. And then I'll graph that. And that says I have to be below that line. I have to be below it. And then finally, the last one, y is less than or equal to -1/4 x plus 6. So again, my y-intercept is 6. And now I have to go down 1 and over 4. Down 1 and over 4. Then this problem, though, it's like you almost find the corner points right away. 1, 2, 3, 4. Some of them, except for 1, is going to kind of give you a problem here. That's why I'm going over it with you. All right, so there. And then we have to be below that line. We have to be below that line. All right, so what's my feasible region? And so I'll shade it in. I'll shade it in. So this is it here. All right. I got to be below that line, above that line, and all the way over here. So we have to find, I see 1, 2, 3. I see two corner points. I don't see the third one. It's easy for me to see. So anyway, let me write these equations. I forgot to do that. That's important. So this is y equals what? X plus 1. Yep, I have to do that. And what was on this one was y equals -1/4 x plus 6. Okay, and so here, well, let's find these corner points right here. So y is -1. So I have a system of equations. One is y is equal to -1, and that intersects the other equation, y is equal to x plus 1. Again, easiest substitution problem you ever have. Set y is equal to y. So -1 equals x plus 1, -2 equals x. Okay, so this is going to be the point then. So x would be -2, and y would be -1. Found that one. That was pretty easy. I want to find this corner point here. So that's the intersection of two lines there. So that's y equals x plus 1, and then y equals -1/4 x plus 6. Again, we said y is equal to y. So I have x plus 1 equals -1/4 x plus 6. All right, so I'll subtract 1 and add 1/4 to both sides. So I have x plus 1/4 x equals 5. So I get 5/4 x equals 5. Now I have to multiply both sides by 4/5 the reciprocal. And then that cancels out. That cancels out, so x is equal to 4. And then if I take that and just substitute it into that equation, I get y is 5. So this is the point 45. Okay, and the last point we have the last corner point is going to be somewhere over here. But you see, now this is why we have to solve a system of equations, because you run off the graph paper. So here we go. So I know that's the equation, the intersection of two lines, y is equal to -1. And then y equals -1/4 x plus 6. So we set y is equal to y. -1 equals -1/4 x plus 6. We subtract 7. We get -7 equals -1/4 x. we multiply by negative 4, we get 28 equals x. All right, so this point, this corner point, though you don't see it, is 28 and negative 1. So we found our corner points here. And so we found our corner points, and they are negative 2, negative 1, 4 and 5, and then 28 and negative 1. We found all three of them. Now all we have to do is evaluate them, plug them into the objective function. Well, with the homework here, so let me show you, this is why I'm going. So the first thing I want you to graph the feasible region for these, and that's what I did. And then I found the corner points for number 3. And then you have to do, so I forget, well, you also have to do 5, 6, and 7, but they go together. And so 5, 6, and 7 says maximize p is equal to 10x plus 16 for constraint exercise 2. Minimize p is equal to 3x plus 5y for constraint number 3. So p equals 3x plus 5y. So let me, px plus 5y. So p equals 3x plus 5y. We have to minimize, so let's find it. So that's 3 times negative 2 plus 5 times negative 1. Negative 6, negative 5 is negative 11. So this is 3 times 4 plus 5 times 5, 12 and 25. 12 equals 37. And then, so 3 times 28 plus 5 times minus 1. What's that? 3 times 24, 84. Minus 1 is 79. Minus 5 is 79. Let me just do that again. 24 carry the 2, 6 and 2 is 8. 84 minus 5 is 79. Now they wanted us to minimize that, right? Yeah, minimize. So then we would choose the point. Okay, 2, negative 2 and negative 1. All right, so that's what you have to do. So I've done 3 with you, 3 and 6. So you'll do 2 and 5, they go together. 4 and 7, they go together. And then you'll do 9 and 10, but then you have to do 12 and 13, because 12 goes with 9 and then 13 goes with 10. All right, and that's where you minimize or maximize. So somewhat of an easy lesson, but you see it takes a long time to do these problems. That's why I'm only giving you 10. So, well, that's it. So carry on.